So dealing with the problem where we have two blocks being pushed across a frictionless surface with a force. And what we're trying to do is determine the amount of force that needs to be applied in order to prevent block 2, the smaller of the two blocks, from sliding down the surface of block 1. Now, regardless, this problem is unsolvable if you do not have a force of friction between block 1 and block 2, okay? Because of orthogonality. Motion or forces or anything that happens in this direction is independent of anything that happens in this direction. Now, force and normal, they do have a perpendicular relationship. So if there are normal forces in this direction, they will produce forces of friction in this direction if there's a coefficient, okay? If it's a frictionless surface, then they don't translate. So in order for a force in this direction to affect motion in this direction, there has to be friction, okay? So looking at the free body diagram for block 2, these are acting, well, the first force. Sorry about that. Getting these announcements and they drive me crazy. The first is normal. I have two surfaces in contact here between block 2 and block 1. If we have two surfaces in contact, we have a normal force. And it's called normal because the vector points out perpendicular. Here is my normal force. Okay? We also have the weight of the block. We have the force of friction in this direction. Now, the force of friction and the weight should be identical. I just ran out of room up top. So this and this should end up with the same value. The normal force in this direction is the normal force. It's what it needs to be. Okay? So, with that in mind, I talk about orthogonality, the independence of forces in this direction with the forces in this direction. So I end up with the equation of forces in the x produce an acceleration that's inversely proportional to the mass. Okay? So in the x direction, all the forces in the x produce an acceleration that's inversely proportional to the mass. Okay? Forces in the y, we've got the same principle. But remember, we're using orthogonality to see. Okay? Cool? Now, talking about forces in the x direction or this direction, I have only one. My normal is equal to mass times without it. And now, that's it for the x direction. In the y direction, I have the weight, which is negative, and friction, which is positive. Okay? Now, there's no motion in between those two. So the acceleration, there's no acceleration between those two, so ma is going to end up being equal to 0. Okay? So real quickly, we can see that the force of friction has to be equal to the weight of the object. Cool? Now, the equation for the force of friction, that's the coefficient, and in this case it's static, because there is no motion, times the normal. Cool? Okay, now, applying this idea into here, I end up with another equation, and I'm going to erase this right now. And I'm equal to the coefficient times ma. I just substituted in for n, ma. Masses cancel out, and I'm left with g needs to be the coefficient times the acceleration. Okay? So in order for this to work, this term right here, well, let's solve for the coefficient. The coefficient is going to be equal to a divided by g. Okay? This term is always something. Coefficients are typically values less than 1. Okay, so that gives you an idea of the scale of your acceleration. Cool? That's one step. But that doesn't solve for the forces that need to be applied to block 1 to prevent block 2 from sliding down. Sort of. Now looking at that force that's being applied to block 1, let's talk about the free body diagram of block 1. Okay? So I need to leave the acceleration was equal to the coefficient times gravity. Okay? Looking at block 1 and the forces that are acting on block 1, I have my weight, my normal, another normal that's being applied by block 2 on block 1. Talking about Newton's third law there. And then force applied. Now, the normal and the weight are going to be identical, but this normal, I should say, and the weight are going to be identical. But the force applied has normal here. If it's not, then this object doesn't accelerate. So I'm going to draw this vector a little bit larger. Okay? So talking about Newton's second law and orthogonality, forces in the x, forces in the y. I'm not concerned with forces in the y because there's no friction. So I'm going to just ignore that term and concentrate on my forces in the x. Well, my forces in the x is I have a normal, and I'm going to be specifying that was the normal from block 2 on block 1. So I draw a little 2 here. And that's negative. Plus, the force applied is equal to the mass of block 1 times the acceleration of block 1. Okay? Well, if you go back in the video and you see what the normal force was on block 2, it was the acceleration of block 2. Okay? And because of Newton's third law, that normal being pushed back on block 1 has to equal the normal that's being pushed on block 2. Okay? So I'm left with m times the acceleration of block 1, or block 2, plus the force applied equals, oh, I forgot the negative sign, the mass of block, acceleration of block. Okay? Now, both of these accelerations are equal to each other. Block 2 is not accelerating faster than block 1. Otherwise, it's flying through there. Block 2 is, excuse me, not accelerating faster than block 1, or not, block 1 is not accelerating faster than block 2, because otherwise block 2 would be falling through block 1. Okay? So these two accelerations are equal to each other. I'm going to move this term over to the other side, and then I'm going to combine like terms. Okay? So I'm left with m2, well, let's do this the right way. Force applied is equal to m2 acceleration plus m1 acceleration, or the force applied is equal to m2 m1 times the acceleration. Okay? And I've already solved for the acceleration to be, excuse me, the coefficient times gravity. Okay? So that's the solution to the two blocks problem.